Welcome to the Cloud Native Containers user group. I'm Lisa, and my co-organizer John is also here. And today we have a special guest presenters. The team that has been sponsoring this meetup, at least the beer and pizza portion of this meetup for the last couple of meetups, is here by popular demand to talk about some of the awesome technology and share their thought leadership with us. So that's exciting. I finally get to know more about the wonderful Opsani, who has been so kind to sponsor our meetup this throughout the the pandemic and the virtual meetups. So John, you want to talk a little bit about the promo? Oh, is your Wi-Fi not?
I will try not to. Sorry if I'm talking over you, because it's like I'm getting a lag. But yeah, the promo, for those of you that are here, and I'll hopefully are aware of it, is that Opsani is giving us a Doordash, giving away a Doordash card to those of you that, or a coupon code to those of you that have showed up here. And we are asking that you please use a real, like a business email, and provide us with your username here on the Zoom meeting, so we can make sure that we're not sending out multiples, which has happened before, unfortunately. And we will, like Lisa said, be adding, if folks come in late, we'll try and just DM folks the information, but the link there. If you have any issues, obviously, the form should work. And Cassidy, as we said, is the person with the keys who will go ahead and make sure that you get it. And in the past, we've been seeing you get it in about 12 to 24 hours. So not quite real time, but hey, maybe we'll get there. Hopefully we'll be there actually in person, and Opsani can actually buy the pizza and beer, which would be much better. And I am not going to try and do much of an introduction, because it seems like presenters nowadays want to introduce themselves and probably do a better job. But I will just say, in full transparency, I have been working with Opsani. I think they're a really amazing technology that they've developed for optimizing applications in a way that just, it's, when you talk about wanting to automate all the things, they really have figured out a way to sensibly automate optimizing application performance and cost saving. And I think we'll learn about that as Amir gets through his presentation. And Amir is their VP of Product and Marketing. He and I have crossed paths many times in a positive way in the past, and I look forward to seeing the presentation, which is always good. He's fun to listen to, and I do hope that, Amir, let folks know if you want questions during the presentation or would like to hold them towards the end. But I would encourage folks to ask questions. That, making it interactive is a lot more fun. You will certainly get a lot more out of the presentation. And with that, Amir, I'll let you get started. And I probably should make you a host.
Presenter, at least. Well, thank you, John, Lisa, for having me, and thank you everyone for coming in. Looks like it's a smaller crowd, so then this calls for interrupt me as you would to ask questions. The chat window is open, so I can see everyone. And just doing a quick sound check. Can you hear me? Can you give me a thumbs up, Lisa and John? All right, that's great. So let's get started. And I will keep the infomercial portion to a minimum. I have to tell you, what is it that we do and why it's relevant? But the presentation is actually a case study of one of our customers and how they used their DevOps pipeline in order to automate tuning. And I think that's an interesting case study, and what the benefits are. It's, of course, our technology, so you can argue that it's self-serving, but it is a game changer. So without further ado, and if somebody can give me presentation rights, please.
Oh, I'm working on it, Amir. Tell a story. The internet is against me today.
Let's see.
Hold on.
As a
Maybe you
backup,
got
you
it.
could also
All right.
maybe send
There we
John.
We got
go.
it now.
We
You
got it. Yeah.
Cool.
No,
All
we
right.
got it. We got it. Just a
Great.
little
Let's
lag.
go
All
and put
right, take it away.
presentation mode. And let me put the chat screen up so I can see questions that are coming on board. I don't know how to do that. So Lisa, if there are questions that are coming up, can you interrupt me? And then we can.
Absolutely. One of us will jump in and ask the question.
Wonderful. So the question here that we want to answer is how artificial intelligence is optimizing or artificial intelligence-based optimization is disrupting the cloud computing industry. And I would say that some marketing person, not me, but some marketing person took a free license of what disruption in this case means. But ultimately, as you will see very early into the presentation, is that we tend to overconsume resources. And that the reason for that becomes easy. So when we say that we're disrupting the cloud computing industry, we're basically making it possible for those who run on public clouds to run much more efficiently, and therefore disrupting maybe the business of the AWSs and Azures. I guess that's the right way to look at this. But giving you kind of a quick overview of what is it that we do. We do continuous optimization as a service, which means that we leverage AI techniques, in this case, machine learning, to autonomously adjust configuration parameters of workloads. Autonomous is like think of a car that drives itself. This is a self-configuring technology that maximizes the workload's performance, reliability, and efficiency. And this is done on the public cloud. And some of our customers that are listed here are Ancestry, Intuit, PayPal, and Adobe. In this case, I'm going to focus on Ancestry and use them as a case study about the transformation they went through and some of the mistakes that they made and what we can learn from them and how they used their CI/CD pipeline in order to increase efficiency and using us to disrupt the billing that they were getting from the AWS. So let's start with one of the paradoxes, and the paradox is staged in twofold. Is the first question is, why do we go to the public cloud? And ultimately, it's because we didn't want to build data centers. They were expensive. And it gives us the ability to go and use resources as we need and consume those resources on the fly and only pay for what we consume. And we do that through the set of APIs, and it makes provisioning super easy, super fast. I'm old enough that the Earth's crust was hot when I was born. And then you had to rack servers. You had to when I was at VMware, for example, it took somewhere between 6 weeks and 2 months to provision a server. And then one of our innovations at VMware was that, now you can do it within minutes. And that innovation now exists within the cloud. So really what we did with the public cloud computing was optimizing cloud infrastructure consumption. Made it really easy to consume those resources, to provision resources. And that's fantastic. That's great. And then we created something called a cloud native infrastructure, basically generally container-based. And that's really to increase the flexibility of engineering and make it easier for our business to change directions and offer new features. Kubernetes has become the de facto orchestration model. GitOps makes it possible for us to download containers quite easily and orchestrate them on Kubernetes. And because of the structure of containers, we no longer have to worry about the OS underlay. Everything is abstracted away, which means that the workloads become portable from space A to space B. It's great. And because it's containers and lightweight, you can scale up really fast and make your software a lot more responsive. And through this sort of changes, we have optimized the app time to market. Make it easier for the app to get to the market easier and for the business to respond quickly. And here's where the paradox is. Great infrastructure, great architecture, but fundamentally you have the underperforming applications which are generally over-provisioned and cost too much. And the answer is, why do we get to this conundrum? Why do we have this problem? And the short answer is that, this as this froyo frozen yogurt chocolate emoji guy says, that this stuff is hard. that it's not easy to do. But that's why your app performance sucks. So let's understand why it's hard. And here I'm going to borrow from my experience at VMware. And when we built VMware ESX, our range of release cycles were quite slow. It took 2 to 3 years for every release to come out. And it was a constraint of problems, which meant that the chipset was known. We know what the motherboard combinations were. We know what the hardware peripheries were. Therefore, we knew what combination of stuff to test. Even with that, the test matrix was quite large, but it was constrained. It wasn't infinite. And with that, we literally had a team of 12 plus Stanford computer science PhDs working on optimization full time. That was their job. Whenever a release came out, they had 2 to 3 years to make it as fast as possible, but it was based on a thematic focus. And it could be the number of IOPS or network latency or whatever it was that we wanted to optimize. For a while, it was really important to get Oracle to run in virtualized environments as well as you could on bare metal. So we knew what problem we were going to solve. The problem space was constrained. We had 2 to 3 years to do it. We had lots of big range. That's what it took to optimize enterprise software. Now the game has changed. We've gone from 2 to 3 years of cycles, and we're trying to get to 2 to 3 days or hours in certain cases with the cloud native construct. And then if you look at kind of the state of the art, you have some guy, who's got a pointy head, and his name is the boss, and he says, "Yeah, I want software. Give me software. I need to have software right now." So the developers very quickly download components, whether it's from the open source repositories or from existing libraries that the company has, and they glue it together. They hand it off to the DevOps team, who builds it, tests it, and integrates it with various subsystems like identity, finance, ERP, whatever they might be. You hand it over to the SRE team, and they take it from the dev environment to pre-prod, run a few tests, and then they say, "Okay, it looks like it's working fine. Let's go. High five, production, it's ready." Except this is where you notice that a problem lags. What you've done is move so quickly through this software pipeline that you've effectively relegated QA to production. You're asking the customer to QA it for you, and the customer starts getting unhappy. And so you put your A team. Okay, with the A team, let's go fix a problem along with the customers. We're going to do real user monitoring to understand what problems they're having. We're going to generate synthetic loads to figure out what the hotspots are, what the choke points are, and we're going to get these really invasive APN licenses that are hard to instrument, but important in order to figure out what the problems are. In the meanwhile, we have a burning bush problem, and the customer is still suffering. So what do? We over provision and already blow the system. Why? Because of the paradox that I mentioned. It's really easy to consume resources. If your software performance sucks, you just give more resources. This is why things cost a lot. Instead of addressing the problem, you have just over provision. It's like, I have an V8 engine, but it's only giving me 50 horsepower. What do? Give it more gas. It's kind of a wrong way to think about it, but this is the way we've approached this problem. And that's precisely because we've accelerated the software delivery pipeline, but we haven't optimized the optimization portion of it. We haven't accelerated the optimization portion of it. This is where the state of the art is. So Ancestry sort of knew this. And what they wanted to do was to standardize software delivery across the platform. Initially, they said, "Okay, we're going to go and go with CI/CD pipeline, but everybody have we're going to go with the cloud native construct and CI/CD." But what happened was that everybody started adopting their own stuff, their own pipelines. So canary deployment from team A to team B, that was a benchmark, was widely different. Some teams took weeks, some teams took days. And because you had a disparate set of tools, global changes were really hard to make. Nobody could really roll out, or the company could not roll out standardized tools across the entire company. And as a result, governance was very difficult. You couldn't see what the costs were, what drove costs. You couldn't develop tools to increase availability or productivity. These were the set of challenges that they had. And then when it came to the pipelines, it's like it was built on old stuff. It's like delivering tar sands from Canada, in the age of the electricity. They were using Jenkins, And every team, as I mentioned, had developed their own pipelines. And the third point is really interesting, is that there were lots of source code changes on the main branch, but not a whole lot of continuous integration. So it's like, okay, I've got this thing, yeah, but I'm going to behave as if it's an old school large deployment, and I'm going to compile the damn thing all at once instead of building small changes and incrementally move forward and making it faster. So there were good teams that had excellent practices, but that wasn't the standard across the company, and hence some of the challenges. And then, when you look at the benchmark, which is the canaries, some teams released in a couple of weeks, as I mentioned. Some teams took significantly longer. I can't say how much longer, but it was significantly longer. And some teams has as many as 40 different systems. And sprinting was, when they call it sprint, it was like, it was a journey. It was a trek. It took a while. And when you multiply this across 70 teams who had an average of 10 systems per, you could see that if you needed to do a larger scale project that involved multiple teams, it was just excruciatingly slow. So taking a step back and seeing, how they changed their, or what the view of their pipeline was. They had this thing that was built, but it was kind of like, everybody had their own. It was a bespoke system, and it wasn't a differentiated system. It wasn't standardized. Everybody could do whatever they could do, and despite having this nice Kanban, the company didn't move faster. So Ancestry took a brave and bold step, and they said, okay, this madness needs to stop. And in the space that it takes for everybody to release a canary, so this is really the slowest team, they said, we're going to put a stop on software releases, and we're going to standardize everybody on the same CI/CD pipeline. They decided to go with Harness, kind of a modern development pipeline, and it was risky. People, I'm sorry, I'm picking up some noise in the background. I think somebody's listening to a commercial. Okay, I muted the person. All right. So basically, they took what appeared to be risky, which is stop software delivery, to standardize their pipeline, and they standardized on one tool, which was great. That pushed up productivity, pushed up efficiency, and happiness went up, because now everybody's working with the same set of tools. Except there was another problem that the company had to deal with. They went from a bespoke system to industry gold, but there was a mental trap. And the mental trap was that, of course, you can't hit all three corners of this triangle at once. You all either optimize for cost, or you optimize for reliability, or optimize for performance, especially when you move fast. So you always have to give something, whether it's a budget overrun or poor performance or errors and restarts. And if you go back to my VMware explanation, with that, we at least had a thematic response. So we weren't trying to do this across the whole platform. We were doing it for specific sets of problems we're trying to optimize. Now, trying to do this for a cloud native construct where you have lots of different containers interacting via API, and it's really hard to know how to optimize. So basically, what happens in this pipeline that we discussed, and this is back to Ancestry, when they over provisioned, they got a little bit more data, and then at some point, they did some manual operations and guesswork, and fed it back to the DevOps team. And the DevOps team was happy to accept these recommendations because they wanted the damn phone from ringing at 3 a.m. I don't know, or pager, whatever it is, Slack, whatever it was at 3 a.m. They wanted to stop going off, and this guesswork was okay. And with enough experience, Ancestry understood that they had the data to have a proper configuration and give it back to the developers. But this change, it took 6 months to a year before they had good enough information to update the configuration file correctly. And but by this time they've had multiple releases already. So it was almost like going down the highway, because now you can deliver fast software quickly, but you're looking at the map in the rearview mirror. You're not looking forward. And that was one of the traps they fell into. It was better than nothing, but it wasn't great. Now, let's understand why it's so difficult to optimize cloud workloads. And to drive the point home, I've basically taken an example from Google, which is their online boutique. It used to be called the Hipster Store, as the canonical example for learning Kubernetes and containers and microservice architectures that when you're learning, when you're a practitioner. So in this case, the Hipster Store has 11 different services. And let's assume that we want to tune CPU and memory for each of these 11 services. So we want to build our software in a way that we have the optimal configuration of CPU and memory for these 11 services. The CPU and memory, 2 services times 11, I have 22 services. And I'm going to step through each CPU and memory setting 8 times. So I'm going to go from, let's say, a quarter CPU to 2 CPUs, and from quarter gig to 2 gigs. And my computation space is now 8 to the power of 22. That's a really large number. That's like Avogadro's number. If you remember that from your high school chemistry, it's basically roughly 75 quintillion permutations. I'm exaggerating. It's more like 74 quintillion, but it's a really big number. And if you're on your terminal right now, just ask Google, say how many grains of sand are on Earth, and Google will tell you 7.5 quintillion grains of sand. This is your computation space. This is how big the problem is if you want to go and search for the optimal setting. So that's one order of magnitude larger than this. And the reason I put this here is because one of my customers asked me with a straight face is, why can I use just a brute force binary search in order to find the right combination? And so he said that, I kind of like scratched my head. I said, okay, look, if you had 10 microseconds to go through each permutation, it'll take you 23 trillion years to run through all this 75 quintillion permutations. The only problem is, sun's scheduled to supernova in 5 billion years. You just run out of time. Don't have enough time. So you have to have a different way of approaching optimization. And so going back to them, one thing they had done, and I'm going to explode this, is they had standardized their infrastructure. So adding new steps into the pipeline was easy. And this is where Opsani comes into the picture, where we can easily add a new service, in this case, Opsani, into what they were doing. So we take the same pipeline that we had, and what we did at runtime, basically, we added real-time autonomous configuration changes. Opsani became a service that was injected in runtime for all services that did auto tuning. And I'll get into how is it that we do this. But we also have the capability of going into the production side, and whenever there's a new build that's pushed out, we can run and optimize that particular build, assuming there's enough traffic. And then we generate a configuration file that gets checked in to GitOps along with the code itself. So this is what I mean by autonomous workload tuning. Is it doesn't matter what the code is. It doesn't matter whether it's in production or whether you're running a test. It's a service that runs in your CI/CD pipeline. It works really well with Kubernetes workloads. It's a repeatable pattern. And what it does, it boosts performance, boosts reliability, and lowers cost. Ultimately, it lowers business risk because the application runs better, the customer's happier, and you spend less money. This is, I guess, where the disruption of cloud computing business comes in. So looking at the results that we produce for Ancestry, they're a large company, roughly 27 billion records of genomics, really important information that's used for disease discovery or searching ancestors and so forth. But really what we did for them was reduce their cost by more than 50%. I'm not at liberty to give you more information. And their performance efficiency, when you measure it in terms of transactions per dollar, that was up by 230%. So that you could do 2.3 times as much for the same dollar that you spend. And that's a remarkable outcome when you think about it. And when we go to the Google Online Boutique, we talked about Avogadro's number here, 75 quintillion. It took us 20 minutes to set up. We ran it for 2 days. The cost of the initial system dropped by 80%. Throughput went up by 71%, increased I guess you can say nearly double, but basically the transaction per dollar, the efficiency of the system increased 8-fold. We are at a juncture where we sort of take the initially set configurations as sort of the gospel. That we said, I'm not going to worry about it. If it ain't broke, don't fix it, because somebody else is going to pay the bill. And when you compound all of these, all of the different services that you develop and you deploy, it adds up to real money. So when you can increase your transaction per dollar efficiency by 8x, you're ultimately saving the company quite a bit of money and lowering business risk and making the enterprise more profitable, making the software more performant. And believe it or not, the error rate also goes down. It's the work that the Stanford PhD guys were doing. Now a machine is doing that. It's like the robots are now even obsoleting PhDs. I'm not so sorry for those guys. They're smart enough to find a different job. But the point is that now there is a service that can reduce costs on the fly for very complex workloads without human intervention. And the way it works is if you take a Kubernetes deployment, basically have various namespaces across the enterprise where the different services are running. There's a tuning pod, for instance, that you want to tune. That tuning pod is where we run experiments, where we basically try different things to check them against production workloads. And when we find the right set of configurations, we promote that into the repository as the best known configuration. And we keep repeating the cycle over and over again. And this, of course, is done as a service. It's a very lightweight servo that's loaded inside your servo or container that's loaded inside your environment. And it just checks for combinations, asks for recommendations from the learning engine that's running as a service in AWS, and comes back, gives you a new configuration requirement. And so one of the possible setups is, for example, is if you, in case you have an Nginx setup, your Nginx ingress and load balancer is a great place to for us to be deployed, because Nginx produces red metrics. We can consume those red metrics to optimize the workloads behind them. And we're doing that in conjunction with F5. And if I show you some of the results, for example, we ran a bunch of different tests with Nginx. The first one was open source Nginx using a sidecar, Envoy, as the measurement point. The second one was using the paid version, again with Envoy, and the third one was a paid version of Nginx. And we used Prometheus, the native Kubernetes construct, to extract the metrics. So because Nginx Plus has a better load balancing algorithm than upstream Nginx, you see the cost reduction is significantly higher. And from the second to third is because we've gone away from the sidecar and using Prometheus, you see that the P50 response time is also better. Error rate in this case didn't change much. It was within a margin of error. If I show you the charts, and you'll see what looks like a big jump, but the scale is inflated. It's like goes from basically near zero to almost zero. So it's not worth reporting on those. And so no real change in error rate, because it went from 0 to 0 in this case for this experiment. And also with App Dynamics, in case you have an APM endpoint, we can use them as a data point or metrics integration point for our service. And we're now partners with APM and taking the application performance monitoring to application performance management for cloud native workloads, meaning that now App Dynamics also modifies the application to manage it, to make sure that you have the right performance in order for you to meet the right business performance requirement. And to kind of give you an overview of how is it that the system works. So there's a service level objective that's either prescribed by the customer, by you, or that's auto-discovered. When I say auto-discovered, is we use the P90 point as the SLO in case it's not discovered. And we have to have an application namespace. And here there's a production replica that we need to have access to. That becomes the control for the experiment. And there's a tuning instance, which is a canary instance, really, where we do the experimentation. And we have our service that's running in the cloud, and we deploy a couple of lightweight containers in the application. we feed the goal, the SLO, to our cloud service. The cloud service then provides some sort of configuration tuning parameters to the tuning instance and sees what happens versus production. And from production, we just get performance metrics. And as time goes on, we continuously adjust the performance metrics, or we continuously adjust the configuration tuning parameters in order to boost the performance metrics. And once the performance comes up to a level that meets the SLO, and then at that point, we start shaving costs. So we're meeting SLO, now let's go for the lowest possible cost. Again, using this constant experimentation method that we have again in a canary versus the replica. And that's done continuously. And here, it's because we're using machine learning technique, it can be done fast and without bias. And we noticed that a lot of configurations that come out are counterintuitive for people. For one of our larger financial customers, the recommendation was to go to larger VMs with fewer instances, which is counterintuitive because typically people think smaller and bigger fleet. But this came with exactly opposite recommendation, and sure enough, this particular customer dropped cost by about 70%. And it runs on any infrastructure. And what this service does is it tunes a single instance, but not only that, but it also tunes the number of instances that you have in your fleet. And knowing the cyclicality of the workload, it proactively auto scales up and down to make sure that you always have the right instances in anticipation of an oncoming load, or downscaling when you know that a workload is coming down. And then the last point is being adaptive for the workload. For instance, late at night, you may run a database heavy workload that's memory intensive. So in that case, the service boosts memory. And during the day, you may do lots of transactions through a web service, and which requires a lot of CPU. So memory goes down and CPU comes up. This is what we mean by adaptive workload. And of course, integration with lots of CI/CD pipelines. But ultimately, this is what we do. And this is how we automate the work that the typical tuning team does. And as I mentioned, when you think about ESX and the miracle that hypervisor is, that it runs basically as good as bare metal. But that took many years of tuning by very smart people and focusing on one problem at a time and a far more constrained problem space. So with that, I can bring it to an end. I'll be glad to do a demo or answer any questions and get your feedback.
Hi, Amir. I didn't see any questions come up during the presentation. If you want to do a demo, that would be really cool, because remember, we are recording this and a lot of people do come and watch it after the fact on demand. So if you have a demo you want to walk through, we have time.
I'll be glad to do that. So let me.
Demos are always crowd pleasers.
Yeah, and I apologize. I didn't pace myself correctly. I may have talked a little too fast.
No worries. And I absolutely loved your supernova slide. That was so cool.
I mean, literally, that was a customer saying, why don't you just do binary search? I'm like, seriously? Okay, so here's my live demo. Let's go to the dashboard. Let's see. Okay. So this is the demo application. Actually, I'm good to start with a summary. So let me explain to you what you see. And first, you'll notice that the progress through this demo is pretty quickly. That it steps through the experiments rather quickly. This is an emulated environment. In a typical environment, the tests would take much longer. Typically, it takes 20 to 40 minutes per instance. Here, we've shortened it to a much shorter duration because otherwise it would be like watching paint on the wall dry. Nobody likes that kind of environment or that kind of demo. But so if you look up top, you see a cyclical traffic pattern. So what we do is we pump various amounts of traffic through the workload to understand how it responds, and it's done through the cyclical load. And whenever we get a good reading, we're recorded as a solid dot. So that would be like one instance of it. But whenever we do a reading, but it's off for a number of reasons, then we annotate that as an empty dot. So the better results are shown as solid dots. And here's the overall system cost. Basically, when we started with the system, the base cost was roughly 4 cents an hour. After optimization, in this case, the cost drops to about 1.5 cents per hour. So it's a 60% saving. And we show you what the performance is for P50, because now it's restarting. Okay, it's good. It's actually a good time for it to restart because you see that the costs are the same. And as it runs through experimentation, these charts will change to the end state that we were just showing. But right now, at the early stages, what we've found is slightly lower. Like here's a solid line, here's a few other solid lines. But in these instances, what we're showing is that the optimal performance is slightly better at P50 and nearly identical at P90. And we keep going through this set of experimentations until we find what the right set of tests are. And here we would record the error rate. But I think the better place for us to look is to go through and watch the experiments as they happen. So you see that if I go to my initial setting, let's see, where do I see the initial setting? Actually, I don't see that button right here, but so I can see that if I go to my highest performance configuration, this is what I've found so far. If I go to my lowest cost configuration, this is what's found so far. And the best performance to cost ratio, this is the most efficient one. And latest, this is what I'm experimenting on right now. And what the system is doing is randomly, not randomly, but it's walking down the set of decision trees and doing various experimentations. And here, the reason we're getting a lot of empty bad points, I suspect, is because the traffic is low. So if I go back here, we're going a low traffic period. That's why we're getting these empty dots. And so over time, we do just lots of different experiments, and we know what the cost is. So here's a point, for example, where I select it, and I see what the configuration is. So and it shows me what the commensurate cost is for that point, and it gives me a score. And the higher the score, the better the results in terms of efficiency are. So I then developed over time a set of different performance and cost lines, and then I know what to recommend. And each one of these data points is a set of configurations that's been tried and tested. So when we get the best one, we can then promote that to production. That would be kind of promote that pushes it into Jenkins, or if you're have enough experience and you want to auto promote this, you just click this, and basically the best configuration gets auto promoted to production, and containers get restarted in a rolling fashion, and they adopt the new setting. So in short, this is the demo, and please feel free to ask any questions. Sorry, I may have had too much coffee and I'm talking way too fast.
I didn't see any questions pop up in the chat. So
I've got a couple questions for Amir though. Aha. I mean, one thing that I thought, so again, full disclaimer, I work with these guys, but I think the technology is really remarkable. And, there are a lot of tools out there that are looking at application performance, kind of APM type tools. And I saw that you're integrated, Opsani is starting to integrate with some of those. But many people sort of treat them as, this is how I optimize my system. I have something that's monitoring it. It's giving me, metrics, and I can just pick the best one. Does Opsani really, obviously you've got the 75 quintillion options, but is the probably out of the optimal or best configurations, it's probably a smaller set than the myriad really lame configurations you could have. Does Opsani really help you produce a much better end result compared to saying I've got an APM, it's giving me, lowest cost or something like that.
Yeah, there were actually a number of questions, and what you asked, one was, are you better than APMs? I think that a second question that you implied was, do you test all the 75 different quintillion options, or is there a way for you to limit the computation space? Do I have that right, John?
Yeah, actually, that second question is one that I'd like to ask, but yeah, I guess the main one was, comparing an APM approach, which seems to be very common to Opsani. What are the deltas there?
Yeah, with APM, the main difference is that APM is simply a monitoring and measurement tool. It doesn't tell you what to solve. It just tells you where the problem is. It's akin to using a thermometer to know if your child has a fever, but doesn't tell you how to bring the fever down. Whereas for us, we depend on the thermometer. We depend on the APM monitoring tools to tell us what the status is, and then we go through a set of experimentations, figure out what the solution is. So the thermometer tells us what the child has a fever, and we go and cut the fever. That to use an analogy. Now, on the second question, basically, it's the way machine learning works is it doesn't explore the entire computation space. Through a set of experiments, it decides which one of the branches on the decision tree are most promising. And it goes and eliminates the rest of the branches, and therefore it reduces the computation space that it has to work on and focuses on what appears to be most promising. And then by constantly narrowing down the computation space and coming down to a decision, it says, okay, this I think is the best one. And generally, the results, I would say it's in our case, in 100% of the cases, the results have been better than a human. But it's not necessarily the case that we found the best possible solution of all, but we found a solution that's far better than anything that people could have done because of the machine learning techniques. As our algorithms progress, currently we're using 4 different ML techniques concurrently to determine what the best decision paths are. But as we get more experience, I imagine the results will just will keep getting better and better.
Cool. Yeah. Perfect. Another thing that I think when I first learned about this was confusing to me was how Opsani is interacting with the application, right? So you're getting the APM, you're getting metrics. It gets sent off to the SAS that is Opsani. It figures out what the configuration should be, and it sends something back to your system. So how is that better configuration implemented?
It's so we like serverless, or we like stateless workloads. The reason is because you can reboot the workload and it picks up whatever configuration that it has, and it starts anew. It doesn't really interfere with what you've done previously. So the way it gets picked up is when we push configuration, basically we are rewriting a YAML file that becomes available to the container when the container is restarted. The container gets restarted and uses the new manifest. It says here the set of parameters that I have. Here's the set of configurations that I have for picking up resources for this particular container, and off it goes. And it runs until we restart that container and redo the experimentation all over again.
Okay, awesome. So now that you guys have had a little bit of a chance to, I don't know how all the questions, if anybody else has one, feel free to throw it in the chat or even unmute yourself and ask Amir.
I think people are still hungover from Memorial Day.
That could be the problem, Amir. Could be the problem.
Believe it or not, I threw out my back on Sunday.
Oh God.
Oh no, how'd you do that?
I was on a roller coaster, and I relaxed. I was like, oh, I'm having a good time showing my kids I had to have a good time, and then I relax, and then you go into free fall, and then all of a sudden you compress. I pinched the nerve in my back. So always tighten your torso on a roller coaster.
Those things are, I mean, they always brag about the like G forces or negative G forces, and I'm thinking that it's not comfortable to put your body through that. That injury is probably not uncommon.
It was fun.
I mean, when you're a kid and your bones are made of jello, you can withstand anything, right? But as an adult, we're injury prone.
But I had a pinched nerve in my back, but I think everybody else has a hangover.
Okay, well, I think, like I said, I mean, we do have some people who have tuned in, but not our usual rowdy crowd. They're probably going to watch it on demand another time. But so I don't know, John, if you have any other things, or Amir, any more wrap ups. Otherwise, we can close out the recording, and then if anybody is still, oh, James is mentioning, really enjoyed the presentation. Sorry, that went away too fast. I really enjoyed the presentation and demo. Thank you, Amir. Well, thank you, James. Thank you for attending. And if anybody didn't get the link to the Doordash gift certificate that our lovely sponsors have generously offered once again for this meetup, then just DM John or myself before the call ends, and we'll post that up again for any of those that were a bit late. Thanks, Jim. Thank you for coming on again. Good to see you again. Jim's a new regular. All right. That is one advantage of doing these things virtually. We've got a nice international and bi-coastal crowd. That is another reason why we record and post everything on YouTube. All right, then. I think, John, I think we can stop the recording. I guess you cut out all the babble anyway, so he's like, yeah, no worries.
And John and Lisa, thank you for hosting this. Really appreciate it.
Our pleasure. Thank you for sponsoring our season. I really appreciate that. And we definitely will hopefully all get together and do this in person again, but we're going to keep some hybrid portion of it virtually, because we have built up a following now that's online only. So we'll see how we can do that. If conferences can go hybrid, I think we can too. So we'll figure that out.
Yeah, and like I said, this is a product where I think it's cool. You know, there's a lot of hype around AI, and I think this is one of the tools where we're seeing, you know, it's really, you know, infrastructure automation at its finest in a way, coming through, and you're starting to see the possibilities that AI present. If you guys, if I can do this, I'm going to try and post the YouTube link. We had a meetup probably 5 meetups ago where Zeta Partners talked about AI in general as well, and Opsani was one of the featured use cases in that. So if you want to get a little bit more Opsani, you know, in sort of a larger context, I think that was a really fun meetup as well.
You can post it in chat, and then for longevity, you can also post it in the chat of this meetup page, just as a comment, which is what I try to do when I'm multitasking these meetups, making sure all the information stays in all the places. And of course, I know you always post the link to the recording in the chat as soon as it's available. Thank you, Kate. Thank you so much for joining us.
Yep, thanks everybody. YouTube link is there, and I will post it up in the meetup page. So, and once we have this recording up on the YouTube channel, we'll also we'll send out an email to anybody that's registered, as well as posting it on the meetup page.
Good stuff.
All right. Well, John, Lisa, everyone, thank you so much. Have a wonderful evening.
Thank you. Thanks, Pierce.
Thank you, Amir. Really appreciate it.
Thanks, everyone. Jeff,
Yep.
Manoj, Kale.
Thanks everybody for showing up.
Thank you.
See you later.